In this video, we're going to be looking at the cross-validation functionality provided by the VectorBT PRO library. What this will allow us to do is reduce overfitting within our backtesting pipelines using a training testing split, much like you may have seen if you've done any work with machine learning, except we're going to be doing this for rules-based backtesting systems. The idea being that it will make our strategy generation infrastructure more robust and mean that we're going to waste less time testing out strategies, either live or with paper money, that are actually not very robust and not likely to perform very well. So to give you an example of the problem that this is solving, I have this notebook here called overfitting.ipynb. It will be with all the rest of the code in the GitHub link in the description. And all I'm doing is I'm pulling a year's worth of 15-minute candles from Binance, just for Bitcoin, just to give us something to work with. I'm then feeding that into this RSI crossover pipeline. So it's not terribly important, the exact details of what's happening here, but it's just a simple RSI crossover strategy where if we go over the upper threshold, we sell everything. And if we go below the lower threshold, then we go all in with a buy. And you can just provide a set of data and a single value of the upper or the lower threshold. It's decorated with this parameterized decorator. And what that allows us to do is use vbt.param here to feed in an iterable. And due to the magic of the parameterized decorator, when I run this, it will run the entire Cartesian product of these two iterables. So it will run every possible combination. So it will run, for example, an upper threshold of 60 with a lower threshold of 20. It will run an upper threshold of 60 with a lower threshold of 21. So on and so forth for every possible combination. Now, I've already run this. It turns out it's 600 combinations overall, which makes sense because there are 30 combinations here from 60 to 90, and there are 20 from 20 to 40. So 30 times 20 is 600. Makes sense. Just a quick sanity check. I'm saving this to this grid variable, which is going to contain everything that this function returns, which is just the Sharpe ratio in our case. So we're testing a whole bunch of different possible parameters for this strategy on a particular time frame, so on the 15-minute bars for that particular year. And this is something that we might do if we were investigating this strategy. We might run it on a whole bunch of different parameters on a specific set of data, and then we can just sort all of these values. So it'll tell us for every single combination of upper and lower, what was the Sharpe ratio that was returned. We can just sort this. It's just a pandas series. And we think, oh, this looks quite nice down here. So an upper of 89 and a lower of 33 is giving us a 2.33 Sharpe ratio. And some people might run off to the bank with that and start trading based on this very specific parameter combination. However, the likelihood is that we're probably curve fitting. We're almost certainly curve fitting here. Although it is possible that this is actually a robust strategy. So what can we do to help fix this problem or help see if our strategy is actually delivering an edge that is repeatable over time? Well, we could test on a different set of data. So this strategy was trained on the 2020 to 2021 data set. That's where we've looked at all these different parameter combinations and we've picked the one that returns the best Sharpe ratio. If this strategy is legit with these specific parameter combos, we should expect it to work at least for a period of time after this training period. Now, it might not work to infinity, but if we're going to run this as our strategy, as our way of trading, then we optimize the parameter based on some previous data, in this case, say a full year, and then we expect it to work for a period of time afterwards. So I've just pulled the next year's worth of data here on the 15-minute candle again, Bitcoin from Binance. And I can just run this RSI pipeline on data 2 with our quote-unquote optimal parameters, and we get a Sharp ratio of 0.86, which is it's disappointing to say the least. We're not getting that above 2 Sharp ratio. Now, of course, this may be dependent on the behavior of the market. So what we can do is we compare the Sharp ratio generated by the strategy compared to the Sharp ratio of buy and hold over that time period. And what we see is, let's say I pull this data 2 here. So portfolio.fromholding.data2.close, and then we get the Sharp ratio. So this is just getting the buy and hold. We see that buy and hold actually outperforms our strategy on the second set of data. And on the first set of data, we can see that the Sharp ratio here is kind of similar to what we get from our optimal parameters. And so really this strategy is at best returning a sort of market level Sharp ratio. It's not doing anything fantastic. It basically just seems to be doing buy and hold. And you could do this test a few more times on different time ranges, but we would probably eliminate this as a potential strategy. Now, I can do this manually. I can pull different data ranges. I can then manually insert these different combinations. And the more splits I have, so the more of these different time regions. So let's say I wanted to test it every month for a full year, or every month for 5 years, or every day for a year. I wanted to do a train test split. This could get very, very messy, and this notebook would be horrendously long. And so what VectorBT does is it provides this data structure called a splitter. So in this notebook, we're just importing everything. I'm suppressing some warnings that come up later on. It's not terribly important. And then I'm generating some open, high, low, close data here for this fictional Chad coin. And I'm just doing this so that everyone has the exact same data that I'll be using. And so we can use this to generate a splitter. And a splitter will automate a lot of those processes that I did manually in that last notebook. So it will split the data into smaller ranges, assign them to either train or test or whatever you want to call these sets. And it's super easy to configure the amount of them that you want. So in this case, I have a year of fictional data. I'm using vbt.splitter.fromNrolling. And what that allows me to do is, let's say I want 12. And that will produce 12 equally placed splits. And they just come one after another for the entire year. Or I can ask for 5 of them, let's say, or 7. It doesn't really matter. I can also specify the length. So length is going to be equal to, let's say, 120. So we're using daily data here, I think, by default. So it's going to be 120 day split overall. Let's set this to a number of days here. So we'll give it something like 120 days. Should be able to understand that. There we go. So that's roughly a third of a year. So visually that looks about right. And then we've got this split here, which lets us choose how much of the data we want to use for testing and how much we want to use for training. So in this case, it's 0.5, which, as you might imagine, splits everything exactly down the middle and generates 2 sets. So for some nomenclature, a set is, in our case, the training and testing. So we have 2 sets in this setup. We have the train set and the test set. A split is each one of these rows. So this data here from the 1st of January to the 29th of April, that is our first split and the data over which we would run our first experiment. And then a range is just one of these. So say this data here from the 1st of January to the 29th of February. So a range is just a particular set within a particular split. I'll be using those names from now on, so you know what I mean. And I hope you can see that if we ran our optimization on this training and then tested it on this testing data, we would have that same setup that I showed you in the previous notebook, except that we could automate it to run on all these different splits. It would be super easy to configure how many of these splits we wanted, how long we want the splits to be. So I can set them to 180 days. Super simple. If you want to change the length of this split, so let's say I want 75% of the data to be training. Again, super easy to do. You can also set this to a negative number. So let's say minus 0.1. If I want the last 10% of the data to be training, testing, everything else to be training, that's also super easy to do. And so I hope you're starting to get excited about the flexibility here we can have with splitters. And then all we have to do is apply this to our existing pipeline, and it gives us a lot of this cross-validation functionality for free. So here's a more complex example we can look at. Instead of just providing this plain old value here of minus 0.1 or whatever you want, we can instead use this split parameter a bit more wisely. We can provide a tuple. So what I didn't tell you is if you just provide a plain floating number like this, what happens is that essentially gets translated into one of these rel ranges with the length equal to that number. And what these rel range wrappers allow us to do is to more precisely specify how much of a particular split should be consumed by a particular set. So in this example, we have 3 different sets, which you may be familiar with if you've used any machine learning tools before. We often have a train, a validation, and a test set. So to show the flexibility of this, I've generated such an example here. And what will happen behind the scenes is by default, this will be read from top to bottom or left to right within this tuple. So the first set is going to get 50% of the data. If we just eyeball this, we can see roughly here that this training set is getting about 50% of the data. The next one is using rel range here, so relative range, with a length of 0.2, which will be interpreted as 20% of the space. And then we also have to provide this length space argument. So I'll show you what happens if I don't do this. Hopefully you can see that this validation set has gotten a lot smaller. So if you don't provide that length space equals all, it will actually just take 20% of the remaining space here, rather than 20% of the overall split. And then if you leave it blank, that will just consume all of the available space. And so what we end up with is a training set with 50% of the data, a validation set with 20% of the data, and then a test set with 30% of the data. Now, obviously, if I didn't want that final set, I can get rid of it like this, and that's all well and good. We'll just generate a 2-set splitter. And equally, if you wanted to do the same sort of thing where you specify how long the test set should be directly without having to mess about with the training set values, you can use the backwards command here. So range, split range quarks here. That's going to be a dictionary, and it's going to set backwards equals true. So that's going to send this keyword argument here backwards to the function that's actually responsible for splitting the range up. So splitting all of this chunk into the 2 different sets. And so now what I could do is I could just set this to vbt.rel range, leave it empty, and have this be 0.2. So have a think yourself about what might happen when I press this button. I'll give you a couple seconds. What's going to happen is that the splitting function is now going to read this tuple backwards. So it's going to look at this one first. It's going to see, oh, we're assigning 20% of the space to the final split. And that's 20% of the overall split here. So we're assigning 20% to the final set. And then this is completely empty, which means just assign everything. So 80% is going to go to training and 20% is going to go to testing. Let's see what that looks like. Of course, syntax errors are abound. But you can see eyeballing this, that looks about right. You can also specify a particular number of days, probably. So I could provide 30 days here. So I want there to be 30 days of testing and then the rest just assigned to training. So let's double check that here. So coincidentally, I've just made that exactly the same as before, which is why it looks the same. So if I set that to 60, we're going from May the 1st to July the 1st, basically. So I believe that's 60 days, roughly. So far, I've just used this from n rolling function here to create a splitter, but there are lots of other functions that you can use to create these custom splitters that have different characteristics, and we'll see a few of them later on. But for now, let's move into actually applying these splitters. So if I just show you what this looks like, so splitter.splits. Under the surface, this is carrying a bunch of slices of our data, and it's storing which indices of our data map onto each split and set. So you can see the first one goes from the first element to the 11,000th element and so on and so forth. And in doing this, I've just realized why when I provided just a straight up value like 150, why these are so tiny. It's because I didn't run this cell earlier, so we're using a different data source that I define later on. If I run that now, it's completely fine. So it's actually using 150 days because the data is actually in daily time format now. I'll leave that back at 60 and let's continue. So instead of using that daily data, it was using this one I defined later on as 15-minute data. That's why things might have looked a bit strange. So anyway, this can be quite useful, as I've just shown, for debugging where exactly the splits start and end. And so it's storing a slice. And so we can use the take function here to pull out particular portions of our data. So if I use splitter.take on data.close here, that's going to pull all of the splits and sets out of our data. Now this is going to look quite strange, but if I just run type on it, we can see that this is actually a pandas series, so it should be something that you're quite familiar with. If I grab the index, you can see what's happening. So it's just a multi-index, and we can index into it by split or by set, so split then set. So for example, if I just grab this here, and index in, you can see we get a pandas series. So it's a pandas series where each element is another series, which is perfectly allowed within pandas. So what this function is doing is it's splitting our data according to however we set up this splitter earlier on. So allowing us to easily access specific portions of the data, which is getting closer to our goal of automating our cross-validation setup. Now this isn't the nicest format in which to read or analyze or indeed backtest our data. So we have this into argument. Now there are a few different arguments that we can supply here. So I think we have stacked is the first one. And what this is doing is it's creating a multi-index on the columns. And now each column represents a particular split. Actually, each column represents a particular range. So each one of these, so this and this, this and this, they all get their own column. Now, The problem with this is that almost every value is going to be NaN. It is to some extent nice, as we could just feed this directly into a VectorBT portfolio object and run a backtest on this right now, because it's in this column-based format. But it's not exactly great for our RAM usage, especially if we have large data sets. It's fine with what we have right now, but not great. So instead, you can use reset stacked here. And what that's going to do is it's going to condense everything down. So instead of the 300 rows we had before, we now only have 120 rows. So it's going to take the data from a particular range and just put it in order in each column. You'll notice that we've lost the time on the left-hand side. So there's no actual clue about what dates that this particular column maps to. But for many strategies and lots of backtesting work, we don't actually need that particular data right now. We can reconstruct it later on. So there's this function here called attach bounds. And if we set that to index, you can see that it's now going to glue this on at the end. So now if I run a backtest on each of these columns, so I maybe do that here just to show you what the deal is. So if I do VBT.portfolio, we'll just run a sort of buy and hold strategy from holding, and we'll use just this whole thing. And we'll just grab the total returns. No S on the end, I think. So you can see here that gave us this pandas series is what this should be if I run type on the whole thing. Yeah, it's given us a pandas series containing the total return for each one of those splits and each range within the split. So this is quite cool. That already gave us a bit of a leg up in automation just by using the splitter.take, which is allowing us to split up the data into smaller chunks. Of course, this is not where the fun ends. We're just getting started here. Instead of doing that manually, having to take the data, apply all these different parameters to it, what we can do is we can just use splitter.apply. So I have a function here which takes in a data object, so some data. It plugs that into portfolio.fromHolding and gives us the total return. So I'll show you just that this is actually working. If I provide data here, I'm just going to get a number for the buy and hold return of the whole period. If I provide data.close, should be the same number. So that's all that's going on with this function. It's a very simple user-defined function. That's what UDF stands for. And so instead of splitting the data, applying the data, etc., I can just let splitter.apply do this whole thing for me. I can specify a particular function. I then wrap any arguments that need to be split with this vbt.takeable. And what that's going to do is it's going to signal that this data needs to have this take applied to it. So splitter.take. It needs to be split up into smaller segments before it's provided to the function. You could imagine if I had a different argument here. So let's say threshold is equal to 5, some random argument, and I wanted to provide that in here. So just 5. And I'll print that out here so you can see what's going on. Let's set that to 50. You can see it's printing that out now a bunch of times. So if I want to provide some other argument to this function, I don't want this integer to get split up into a bunch of sections. That doesn't make sense. We only want that to happen to time series data that needs passing independently. So that's why we have to wrap it with this takeable here. Just to signal to VectorBT what we want to happen. And then merge function equals concat. What that's doing is it's specifying what we want to happen once we've calculated all the results. So we use the splitter and we split up all this data into these different splits. So you have all these columns looking like this. Some data structure which looks like this. Now, we're going to apply a function to all that data, and we're going to get something back from that. Now, in our case, it's just a simple integer. And so concat works very well in this case. It just concatenates them all into this series. If I get rid of merge function here, you'll see what the default is. So the default is that we have one of these weird pandas series. So you have your split here, and if we go into it, 0 and train, you get this nested pandas series. Whereas if we provide this merge function of concat, it concatenates all those series together, and you end up with a nice unified series. Now, this is going to be a problem if we don't return a single value, but instead return, say, a full series. So if I do returns instead of the total return, and I run this function, let's give it a run. So buy and hold return. I run this on data.close. I'm going to get this full series, which tells me the returns on a particular day. And I'm not entirely sure what's going to happen if I try and run this, but it's not going to be pretty. I'm getting some error here. So instead, what we can do is we can provide column stack here. And that's going to now put them into these separate columns. And you can do the same thing, I believe, where you can apply reset to it. And now, it's a much more condensed data frame, but we have lost the bounds here. I think it should be the same argument if we want to add them in. So attach bounds equals index. Yeah, same sort of idea as we used with take earlier. So that's splitter.apply, and how we can use this to apply a user-defined function for a particular splitter on each range. So this could be quite useful even outside of cross-validation. If you need to split up some time series data, apply a particular function to each segment, merge the results together. It's doing a lot of work, which could be useful in a variety of different projects, not necessarily backtesting. Okay, so that's kind of, to some extent, digging into how splitters actually work and how they can provide increasing levels of automation. One slight issue with this so far is I've been referencing this splitter object this entire time. So I've been doing splitter.apply, splitter.take. Now, that requires you to have created a specific splitter already. And when we produced these splitters, we provided this index argument. So the index is obviously the index of the time series data that you have. So I'll just show you what that looks like. So data.index. Now it doesn't care about the columns, it only cares about the index. So if I data.close, it's just all this gubbins on the left-hand side here. That's what it's after. Because once it has the index and it's split the index up into certain segments, it has everything it needs. But it needs this index in order to do anything to your actual data. Now the problem is, if I have a separate set of data and I want to apply all of these same parameters to it, I'm going to have to create another splitter object, and that's annoying. So what we can do to solve this problem is there is this at vbt.split decorator here. And you can provide exactly the same argument. So you specify the splitter that you want. You specify the keyword arguments. So that's just going to be, broadly speaking, whatever you would put inside here. So all of this stuff. You stick that in the keyword arguments dictionary. You can also specify this takeable args here. So I can say, from this particular function, I want data to always be wrapped with this vbt.takeable. So I don't have to remember to do it myself. And that will automate that process for us. We specify the merge function, the same as we did with apply. And of course, you can attach the bounds if you want to. So this is going to do the exact same thing. It's just going to automate the creation of a particular splitter object using our particular data. So if I wanted to, I could slice this data up if I wanted to. So I could specify I want to get the data from 2020-01-01 to, let's say, 2020. Let's just run it till like November time. September time. So -01. And this is going to create 5 different splits, and hopefully it should work. So we have 5 different splits, and we can see that the last one ends on the second here. Now, it ends on the second because this is exclusive, so this last date is not actually within the range. But I hope you can see that that's working now. So if I provide, 05, it's going to do the same thing. It's going to make these 5 different splits dynamically based on the particular data that I provide, rather than relying on having to create these cumbersome split objects all the time. And you can use this VBT.split decorator to decorate, any function that does anything really, although we're going to be mainly using it for backtesting pipelines. One thing that you can also do that I didn't say earlier is that you can override arguments within this split decorator. So I've provided some very specific arguments here, and I might not want to use exactly, say, 5 splits every single time, or I might not want it to be exactly 50-50 every time. So you can provide this as a kind of default, and then when you're actually running this function, you can override these values. So if I go down here, we can see, in this case, I've overridden some of the arguments that get sent to splitter.apply. So it's going to create a splitter. It's going to run the apply function like we did manually. And what I can do is I can override particular arguments from there. So I can specify that I only want training sets, and I want you to merge all of those in column stack format, and I don't want you to attach the bounds. So I've overridden this. If I get rid of it, you'll see that the default kicks in, and it'll attach the bounds because we specified them over here. And so if I don't override that, what's going to happen is we're going to get these bounds attached. I can also change the number of splits. So I can do something like splitter quarks is equal to dict n equals 10. So what that's going to do is it's going to merge this dictionary that I provided with this dictionary, and it's going to overwrite any new values I provide. So this 50-50 split will remain exactly the same. The set labels remain the same. It's just going to overwrite this because that's what I overwrote. And if you didn't catch what I'm doing, I'm providing this sort of underscore before the name, and that's going to signal to the decorator that I'm providing an argument to this decorator rather than to the function. Of course, we don't want to pass this dictionary to the function. We want to pass it to the decorator itself so that we can dynamically override some values. Again, we don't want to be creating 50,000 different versions of this decorated function with different values. We keep this as a kind of default. And if we need to override anything, we can later on. It's no problem. All you have to do is use something like this. So again, if I wanted the test set, so let's say I didn't really care about training, I just wanted the test set, I can do that. Instead of column stack, I reset the column stack. And now it's going to give us this. So I hope you can see how cool this level of automation that we're getting here is. Now let's run some real backtests. So far I've been just doing sort of buy and hold returns type things. Not the most riveting thing in the world. Let's run a real pipeline. So I'm going to generate more data this time. This is the one that I accidentally showed earlier. We're running 15-minute open, high, low, close bars generated by geometric Brownian motion, and we're using the same seed so that you'll have exactly the same data that I have. I'll show you what it looks like. I can just do that. It's going to look something like this. You'll notice I'm now using a new function. So I'm using this CV_split. So it's not vbt.split, it's vbt.cv_split. But you'll note that I'm providing essentially the same values here. So I'm providing, broadly speaking, the same values to this decorator. We have the splitter quarks, the merge function, which arguments are takeable. The only real difference is I'm providing this return grid function, or parameter rather. I'll explain what that does in a second. But what this vbt.cv_split function is going to do, this decorator, is it's going to automate that manual process that we created earlier. So right back at the beginning of this video, in this overfitting notebook, what I did was I went to a particular section of data, I grabbed all of the results grid, I looked for the best value, and then I ran that on the training set. What this is going to do is it's going to automate that whole process for us and run it on every single split. And so I have this RSI pipeline here. It's exactly the same one I showed you from the overfitting notebook, so I'm not going to go into the details. And what's going to happen by the magic of this decorator is it's going to run a parameter grid. So a Cartesian product of a bunch of different parameters. So exactly like we did before, it'll run, a value of 60 with a value of 20 and a value of 60 with a value of 21, etc. So it's utilizing that parameterized decorator that we saw earlier, but it's combining that with the split decorator. So for each split, it will look at the first set, so in our case, the training set. It will optimize and pick the best value from that, all the different parameters. It will create a Cartesian grid of all of those, and it will return the particular parameter selection with the best outcome. Now, the best outcome by default is the maximum. So we're returning the Sharp ratio. Obviously, we want to return the maximum option. There's this parameter here called selection. Now, that can be maximum or minimum. By default, it's set to max, so it's looking for the highest value, and it will consider that optimal. But you could also set it to minimal. You can also provide a template here if you want something a bit fancier. So if you need some custom function to determine the best result, maybe you average out a bunch of parameters that are close to each other to look for robustness, you can do that there. So if I just show you how I'm invoking this, I'm running RSI pipeline with my data and these different parameter ranges that I showed you before. So we're running from 70 to 80 on the upper threshold and 20 to 30 on the lower threshold. You'll notice it's returning two distinct items here. So it's returning grid and best. I'll show you what these look like actually. So if I'll just run this. Might take a second or two because we're running hundreds of different combinations and then splitting those, etc., etc. But what we're going to end up with is something that looks a lot like this. So we have this best here, and what best is going to do is it's going to give us whatever the best parameters happen to be in the training set, and then what happened in the test set. So in this case, we can actually see that, in this particular split, we actually got a better Sharp ratio in the test set as we got in the train set. Now, of course, this can be due to simply having, more of an up market in this split. So we don't want to place too much stock in that. You can see what happened here is that it optimized on this split, on this particular range here, this training range. It got a really high Sharp ratio, and then it ran it on the test range, and it got a negative Sharp ratio. Equally here, it got super high value for the training, and then not very good for testing, etc., etc., etc. We also have the full grid, so this grid option here. That's going to give you, all 800 different results. So for each split, each set, each parameter combination, it has the whole thing. That's what this is doing here, this return grid equals all. I like to include this so that if I want to examine this grid later on, I have it available to me, or I can just look at the best results and how they performed. One thing that is helpful here, so obviously this is, it's providing these sort of magic results. One thing that can be helpful is there's this really nice functionality here where you can just provide an argument here called return splitter, I believe. Return splitter equals true. Splitter.plot. And so if you remember, it's using these arguments to dynamically create a splitter depending on your data, but this can sometimes be hard to visualize. And when you're looking at these splits, you kind of want to see, you know, this particular split, what time frame does this correspond to, etc., etc. You can use this to just grab the splitter from the pipeline and then plot it out so you can see, oh, you know, this split didn't do so well, this split did really well, this, you know, you can see if there's a particular pattern there, you know, maybe you're in a particular regime that might give you some idea of what's happening. You know, so like, why are these quite correlated, whereas these are very uncorrelated? Why are these particular splits doing well? You know, they're doing well in both in train and test, whereas this one is not doing well in test, this one is not doing well in test. It can be just really helpful as a visual indicator. It looks like I had the same idea here when I created this notebook, but what I can do is I can create like a benchmark here. So I can do something similar to what I showed you before, where I run the whole thing on a on the data that we take from this splitter that we've created. I run from holding on it, I generate the Sharpe ratios, and that helps me have some context around how my strategy performed versus how the market performed. So I can compare these values here. So we can actually see in this first split, the market returned a Sharpe of negative 1.58, whereas mine actually returned a positive Sharpe ratio. So you can see here, you know, if the returns of your particular strategy are just due to market fluctuations or whether it's something more robust. We can see that in general, these are all over the place. So in the first test set of the first split, we had a negative Sharpe ratio on the bench, and yet we had a positive Sharpe ratio with our strategy. But in the next one, it's the opposite way around. The benchmark did really well. Our strategy had a 0 Sharpe ratio, essentially. So it's not providing consistently market-beating results, which is, again, you know, another pointer that this strategy is not robust in any meaningful way. So far, we've just been using the built-in splitter, the from n rolling splitter. And that's all well and good for certain types of tests. But what about if you want something a bit more complex? Now, there are other default splitters built into VectorBT, and I encourage you to go out and try them and have a mess around with them. But in general, I find building a custom splitter myself a lot more easy to precisely control what's happening and how the splits are generated. Now we can do this with a custom splitting function. So it takes in a bunch of different parameters, whatever you want. There are some built-in parameters that you can provide. So this index is going to feed in the actual index from the data. This previous start is going to feed in the previous start of the last split. So whatever the last split was, it will feed in the start point of that last split. Equal with previous end, it will feed in whatever the previous endpoint was. And then, of course, you can have your own keyword arguments. And there are a bunch of other context variables, that's what these are called, that are available. So you have the split IDX, which is the current split index. The splits, so all of the splits that have been generated, the bounds, all of the bounds, you know, previous start, previous end, which I'm using, etc. And so in the end, what you want to return from this function is a list, or probably just some iterable, of slices. So this split function can be any regular Python function. It takes in these parameters, it returns a list of slices, which is going to represent a particular split. So what I'm saying is if previous start is none, which means that, you know, there is no previous split. If this is the first split, then what I want to do is I want to start the current split at whatever the first timestamp is in my index, plus the frequency of the index multiplied by some offset. In my case, I want to have a little buffer at the beginning. So I think I have a picture down here. So I want to have a little buffer at the beginning so that all of my indicators can be warmed up before we do any actual CV. And then in this next line, what I'm saying is basically if it's not exactly the start of the month, so if it's not midnight on January 1st or midnight on February 1st, just add a month and then make it midnight. Which is why, so the data that we actually have starts on January 1st. We add a bit of an offset to make sure that our indicators can be warmed up. But then we're no longer on midnight on the 1st of January, and so we skip to the next month's start of midnight. Again, this is just an example, but I hope you can see how powerful this is. In order to get the end of this split, so the end of the whole split this is going to be, I add 1 month to it. And so that's going to give us our sort of fake previous split here. So we have this fake previous split, which is going to go forward a certain offset, and then it's going to skip to the first of whatever the next month is, and then add a month to that, and that's going to be that range. That only happens on this first iteration where we don't have any previous data. After this executes, we add another month to whatever the previous end was, which means that in effect, our total split is going to be 2 months long, as you can see. So, this is running from the 1st of February to the end of March. So it's about 2 months long. And then we just do a simple check to check that, if the new end, so this new end, if it's bigger than the last element of the index. So if we're going out of the range of our data, return none, which is the sign for this to stop executing. Otherwise, return this slice here. So it goes from previous start to new end minus some particular amount of time. So in this case, I'm assigning 2 weeks to test, and that's going to be assigned to this slice here. So this is going from the end minus 2 weeks to the end. This is going from the start to the end minus 2 weeks. Hope you can see how this function's working, how you could write your own, and all the different options that we have. It's very, very important that we add this keyword argument in here. So we had the from n rolling earlier. This is from split func, so it's going to take a custom split function and it's going to convert that into an actual splitter object. Very, very important that I use this index bounds equals true, because that is going to give us actual timestamps here on the previous start and the previous end, which allows me to do, a lot of stuff like this, like checking if it's equal to a particular pandas timestamp. If you don't do that, you'll probably end up with integer bounds. So it'll tell you now, this is the 4,000th element to the 6,000th element, which for our case is less useful. We can also just provide arguments here. So I can set test weeks equals 4, override this particular argument. And I'm using a template here, so vbt.rep. So what this is going to do is on each split, it's going to replace these templates. So that's what rep stands for, replace. It's going to replace these templates with the appropriate values. So it's going to grab the index from this argument here. It's going to do a bunch of magic in the background to make sure that we receive this full index into this function. And then equally, we have those that I talked about earlier. So these are just provided to us. If you look in the documentation, you'll see this list. These are just available in the context of this function. It knows what these values means, and it will substitute them in. Other than that, everything looks pretty much the same, and we have this now fancy custom splitter that we can use with arbitrary logic. This is very similar to the from expanding splitter, but there are a few differences in that it forces us to start on the first of the month of a new month after a certain offset. We have a configurable amount of testing weeks, etc. You probably could get the default splitter to conform to this logic, but I just wanted to show how flexible this is, and so that you don't have to memorize the syntax for 10 different inbuilt ones. You can just build your own. So let's actually apply that now. So we're using the CV split again, But instead of from end rolling, we're using from split func. And then broadly speaking, you can just copy and paste everything that's happening in here into these splitter quarks. That's going to get fed straight into from split func. Takeable args, return grid. You're familiar with this by now, and this is using the exact same RSI pipeline. So what I can do is I can feed that in to our setup here, and I'll also, just to save time here, I'm going to override the apply quark. So remember, we can override particular elements of CV split. I'm going to override this apply quarks and just select the first split. That'll just save us time calculating everything. Splitter does not expect arguments split quarks. Maybe it's because I haven't run this. So I've named the functions exactly the same throughout this notebook, but you've got to execute them in a specific order. Yeah, there we go. So that's just giving us the values for that particular split. If I comment that out, it will run all of the splits. But again, it can take a couple seconds because, you know, we're running sort of 100 different combinations on each split, and we're using a lot more data than we used earlier because we're using this this 15-minute data that I generated. But later on, I'll show you how to speed this up using multi-core processing. Now, as a final sort of step here, I want to utilize this offset that I created. So I made sure that our splitter always has some empty space at the beginning. And the reason I want to do that is because I always want to make sure that my indicators are ready at a specific point. So, for example, when we start in this this range here on March the 3rd or whenever it is, I want to make sure that we have all of the RSI values at that time like we would actually have in trading to make this more realistic. Because if we just do a normal split and we only feed in the data for that point, the first 14 values are going to be null, which could actually be important in terms of the realism of the backtest. So to fix this, it's pretty simple. So this is broadly the same as it was before. All of these CV split things pretty much exactly the same. Sorry, we're going down here, aren't we? Indicator warmup. So what we changed in CV split here is instead of making the data takeable, so instead of allowing this decorator to split up all of our data and pass it in chunk by chunk into our pipeline, we discussed why we can't do that before, because it only has data to the start of the chunk, but we need extra data to glue onto it in order to allow our indicators to warm up. So instead what we do is we set takeable arguments equal to none. So we do nothing takeable. We still need to tell it where to get the index from though, because it needs an index in order to generate a splitter. So we say index from data. Everything else is pretty much the same. I'll just change this to true to make sure everything is actually the same, or all rather. So instead of splitting up the data and allowing the machinery of CV split to do that, instead what we're going to do is we're going to use one of these context variables called range. Range with an underscore because range itself is a reserved keyword in Python. And what this allows us to do is to take this range into our function here. So range is going to get passed in using vbt.rep. So on every single split, this range will be passed in. This range is going to represent the whole split. And it's going to be passed in as a slice object, which you may be familiar with. And so what I'm going to do is I'm going to take this variable, this window length. So by default, most RSI is 14 windows. I'm going to construct a new slice based on that slice. So it takes the start point of the slice. We go back 14 points, make a new slice based on that. We're going to use this slice to index into our data. And this is going to give us a slight buffer on the start of our data. We made sure with the splitter that there was always data available before that point. And so we're very safe to index into it here. And then broadly speaking, everything's exactly the same. So we run the RSI, we run the entries and the exits using these crossed above and below. We just remember at the end that we need to chop off that extra data. That extra data was purely for our indicators to warm up. Everything else is exactly the same. And the only difference is we just have this extra argument here. So this vbt.rep range, everything else is exactly the same. So let's run this and run this. We're running quite the parameter grid here, so this might take a few seconds, but I am only running it on the first split here. Okay, so we've got our results. They probably won't be any different from the non-warmed up version, but you could imagine if this was, like 300 window, that could make a real difference in terms of the realism for warming up our indicator. The final thing I'm just going to show you here is how we can parallelize this test. So as you saw, this was kind of slow to execute. It wasn't great. It took 20 seconds to run one split. You might be running 20 splits. So the thing we can do is we can use this execute quargs here. Now, because CV split is essentially a combination of parameterized and split, so the two decorators I've shown you throughout the video, this is kind of a combination of them both. Both of those take execute quargs as a keyword, and that will have different results. So what we can do is we can pass this to parameterized quargs, which will overwrite in here, parameterized quargs. It will overwrite that. And so we can send these execute quargs directly to the parameterized decorator. In essence, what this will do is each split will be executed serially. So it's going to chop up all of the data into testing and training and on each particular split. And then each one of those is going to be fed serially, so run one by one. But the parameter grid is going to be split up into X amount of chunks using these arguments. So what this does is it uses PathOS, which is a multi-processing library. So it'll be running multiple Python processors to calculate the results. It will chunk the data. So we're generating 400 different parameter combinations here, 20 times 20. It will chunk those into some amount. Now, by default, this is going to be the number of cores on our machine. So maybe if you have a more powerful machine, it will generate more processors. And then, so say if I have 20 cores and I have 400 combinations, then each core, each process is going to get 20 of those combinations. It will run them serially on each core and return the results to us. That's what's happening here. It's going to split up the data into the different ranges. So for each split, each set, etc. So say the first set of training data, it feeds that into the parameterized decorator, much like what we had over here, except the data that we provide is just going to be, the data for that particular split. And then this function here, this function is going to be distributed over a number of cores using multiprocessing. And so we should see a pretty big speed up here. Let's just try one split for now, and let's see what that's like. You may be able to hear the fans on my PC in the background. They sped up significantly when that happened. So yeah, we're down to 2.2 seconds. I can't remember what it was before, but it was a lot higher than 2.2. And again, I can comment this out, and we'll run the whole thing. So it's running these splits quite quickly, as you can see. And so an alternative here is that instead of passing these to parameterized quargs, you can just pass it directly to CV split here. That's going to end up getting passed to splitter.apply. And so if you remember what I said before, with this one, each range is going to be executed serially, but the parameter grid is going to be distributed among the cores. With this one, we have kind of the opposite situation, where each core is going to get a particular range. So it's going to split up the ranges among the cores into chunks. Now, by default, it actually does this in a particular order because, you know, it wouldn't make sense to calculate the test before you do the train, right? It needs to be in a certain order for cross-validation. So it's going to take all the splits, it's going to distribute those to each core, and then each core is going to crank through first the training set and then the test set on the full parameter grid. You can use this option. It may be quicker or slower. I haven't benchmarked it. But if you have a very large parameter grid, you might end up with some RAM problems because it's going to try and generate that parameter grid on a much, you know, however many cores you have. So it might do that 10 times. We can run it. I believe it has sort of similar speed. It's not vastly quicker. You'll have to experiment to see what works for you on your machine. But in testing this, I did actually have my computer freeze on me and run out of RAM when I used this one. So yeah, do your own experimentation with this. And so with that, I think I've given you a solid introduction to cross-validation in VectorBT, how you can use it to do your optimization on a training set and then run that on a test set. Or indeed, if you didn't even want to do this optimization, you could use the splitter just with one set. So we could generate some sort of splitter over here. We can just get rid of this and do this. You can just generate a splitter like this, use splitter.apply, use @split, whatever you want. And this could show you, for a particular parameter combination, how your returns look like on a rolling basis or something like that. So there are lots of different applications of these constructs within the library. And I hope I've given you the tools to try this out for yourself. As always, code is in the description, and I'll see you in the next video.